Hi everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire, and today we've got Matthew, who has just completed the course ROS Basics using Python, and he will be giving us a presentation on that. So as always, we'll begin by seeing a demonstration of his code base running on the real robot, and then after that we'll get to ask him a couple of questions, or my favorite approach, ask as we go. Therefore we get to understand immediately why he made the decisions that he made. So without any more wasting of time, let me hand over the platform to him so he can begin his presentation. Matthew, whenever you're ready.
Cool. Thank you very much. Let's hope this works. The objective of this program, first it calls a service server to get the robot to move to approximately 0.3 away from the wall. And then the goal from there, it activates a action server to passively keep track of odometry data, like, hey, I've traveled this far, that sort of exclusively that sort of thing. And then up, you'll see now it's taking that corner. Just hoping it doesn't clip anything. Oh, gosh darn it, clipped the wall. It's part of working with a real robot. So anyways, you're probably going to see the service server part of that a couple times. Just the bit where it rotates, goes to the wall, rotates back. The objective of this code, or of this exercise, is to make the robot navigate this environment at a distance of approximately 0.3 from the wall on its left-hand side. So just make a loop, and then when it gets back, it prints a big list of points that it's been to. So it's like, oh, I was here. And then you can use that data for stuff. So why did it corner there? Oh well. Part of the difficulty with this program is the real robot starts in a different position each time, whereas the simulated one is perfectly 90 degrees relative to the wall. But at the same time, that could just be an indication of lack of code robustness. I don't know. This should be the one.
Yeah, let's see if it manages to avoid the corner.
There we go. Now it's cornering with plenty of distance. It should be detecting after the post corner that it's too close, so it's turning right. And then it should be straight out here soon-ish. It just took that corner really well. Very happy with that. So now you'll notice it's starting to turn left again to correct itself because it's too far away. Should be cornering here again any second now. It might have turned too far. It's probably going to clip the wall there. Yeah, rip. But that's the general gist of it. Depending on specifics of the situation of where the robot starts and that sort of thing, it can occasionally get itself into a little bit of a pickle. But such is working with a real robot, as I understand it.
Did it at least manage to complete the loop when you were testing?
Yes, it has. I wouldn't dare request a presentation time slot otherwise, because that would be like, oh, I'm wasting someone else's time for no reason. I mean, it's a little scuffed, but it's doing it. It's going to corner here.
Ideally, it's supposed to keep the distance that is required, right? 0.3 from the wall, and
Ideally,
keep
yeah.
within those bounds. So plus or minus 0.05.
But yeah,
Right now, it's veering way too far away from there.
Yeah. I mean, that's, as I understand it, partly because it cornered early. That's more my mistake as the person who sets up the robot for execution. Because if it's turned um, slightly left, it can sometimes mistakenly read, oh, okay, um, oh, hey, it did the thing. Here's all of the points. Um, I couldn't figure out a better way to get them other than just dumping them as one giant log. Um, so here those are. And if you had been paying attention to this during execution, you can go back in the video. There might be too many points for me to actually pull up the logs. Yeah. It'll spit out every now and then, oh, I've traveled this many meters so far. I've traveled this many meters so far, amidst the other stuff. Anyways, back to what I was saying. It cornering early there was resultant of a mistake on my part, where if it, um, after the service server completes its motion, if it's facing slightly off kilter to the left,
Mm-hmm.
um, this can create a situation in which the sensors believe there to be a corner, because the front sensor is detecting something within zero point 0.5, if I'm not mistaken, which causes it to corner. But one thing I'm actually very proud of this implementation is, as you saw, it recovered from that quite elegantly. It did end up kind of winding out very wide and going outside of the zero point 0.3 threshold, and it even had a weird corner thing here. But once it got onto this half of the track, it was able to adjust, compensate, and stay within the allotted distance.
Mhm. Can you at
So,
least be able to pinpoint what exactly is going on when it goes out of the bounds that we wanted to stay
oh,
within, right?
yes, no, absolutely. That's what I was saying about it. The service server gets called to move it to zero point 0.3 away from the wall.
Mm-hmm.
And if the robot's starting position is not such that the front is directly perpendicular to the wall,
Mm.
but rather if it's facing towards the wall slightly, this can lead to a condition where it mistakenly detects a corner at a certain distance.
Mm.
Um, it's like, oh, there's a corner here. The logic says I need to turn. Um,
All right. So
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 that's
your wall follower algorithm, is it making any compensatory measure to like cancel that effect? Because I'm thinking
so
if you had figured that out, or you do happen to know about it, why didn't you implement that mechanism to cancel that out?
so the thing about my cornering logic is I have it working. Um, it works fine on normal corners. And considering, so this situation only arises in cases where I, as the human, make a mistake. Um,
What do you mean? What do you mean?
my, Specifically in positioning the robot starting position such that the front isn't perfectly 90 degrees, because that's the only situation in which case that will occur.
Yeah, but
In a
the
situation,
I think the whole point of having to implement this autonomous, like the system that allows your robot to follow the wall, is for it to be able to make corrective measures on its own, right? So despite the initial conditions, right, they cannot be that accurate. Like you cannot say I'm gonna measure 90 degrees and make sure that it's completely perpendicular to the wall that it's facing. It's gonna be very difficult for you as a person, right? So roughly you're
yes,
supposed to localize it well enough but not be that accurate, and the robot will make compensatory measures on its own. That's why I'm saying I think that.
which also it did. Um, Once again, the compensatory measure, the compensation measures. I don't know how to pronounce that word you just said.
Compensatory.
Um, Compensatory.
Right.
Thank you. It did perform those measures such that during the second half of the loop, it did follow the wall at approximately zero point 0.3. You know, there's a little bit of wiggle back and forth as it was adjusting. But
Okay.
that's kind of another reason that I wasn't like, okay, this is debilitating. It was like this doesn't come up that often. And even when it does come up, the robot is able to fix itself to get back on track. So
All right, all right.
yeah,
Let's see the implementation of the wall following algorithm.
of course. So source wall follower, wall follower, wall. You said of the following
Yes,
itself
wall follow.
specifically.
Right, that one.
Okay.
Yes, can you run
So,
through that one?
um, first, right off the bat, I have a whole bunch of variables I'm using to store like Booleans, distance values, time delay values, just things that I'm going to use later on in my code.
Mm.
In my init, here is where I build my odometry client. That's the action server.
Mm-hmm.
Here is where I set up the service server, which is what gets the robot to turn, to face the wall, go to the wall, and then turn back. Um, Here I have a timer calling command velocity callback. Basically, what this does is it gets the robot to trigger the movement logic every 0.5 seconds.
Mm-hmm.
Actually, I need to update this comment. Whoops. Here's my laser scan data. Here's my publisher to get the robot to actually move. And here's a interesting thing I had to do. I have to wait for all of the servers to get ready on the real robot, which actually takes time. Whereas in simulation, all of this stuff boots up at the same time, so you don't have to worry about them stepping on each other's toes.
Okay.
With this, I was running into issues for a while where it was trying to just move forward and then the server would activate, and it was causing all sorts of problems. Um, so here's a send request to wall finder. Here's the response for, or here's a function to handle the response for the service server that causes it to go to the wall. Getting odometry data, feedback, or here's the request, here's the feedback, here's the response, because action servers give constant feedback, but when a certain goal is reached, they also give a response at the end, like, yay, I'm done.
Mm-hmm. Yes.
So that's what that is. Here's my velocity callback. This is what actually causes the robot to move. So if not service server done, it just returns. Flat out, don't move yet.
All right.
After the fact, I also had to add a 2-second delay, just so that we were absolutely positively sure that everything related to the service server was done before it started moving. If it hadn't gotten a new LiDAR scan, it was also going to return because I need new LiDAR data every time through in order for it to move or act intelligently. And also, this is, what does this correspond to? This also corresponds to wall finder again. So I extract front and left. These correspond to a beam out the left-hand side of the robot and directly out the front. These are all that I needed. Future implementations could potentially break front into like front left, front, and front right.
Mm-hmm. So right now you're only dealing with the front, is that right? You're not even considering what's on the left or on the right.
So I have front and I have left.
Okay.
But those are the ones that are pertinent to me.
All right.
I chose not to collect data from the right because depending on whether or not it's driving past an obstacle, depending on whether or not it's turning, that data is going to change very wildly and potentially unpredictably.
But
and it's like, okay, I can't do anything.
Right. But don't you think that would have helped in your wall following behavior? Don't you think that would have made it exhibit a better form of following, like staying within the bounds that we want?
I don't think so because just because it's within 0.3 of the wall on its left-hand side, it doesn't necessarily tell me anything about how far away its nearest right-hand side LiDAR is supposed to be. And when I say right, I mean directly opposite the left, like out the right-hand side at 90 degrees relative to front.
Oh, yeah, I do. Yeah, I understand that bit. I'm thinking about corrective measures, right? Because from what we have observed, we see that um, it does some form of corrective measures, right? But they seem to be not so proportional to the error that it's getting, right? So it seems to be over rotating when it's supposed to just rotate a little bit, right? So when you have that um, extra sector, for example, let's say, you might be able to maybe correct a little bit better. That's what I'm trying to
Yeah,
nudge
no.
you towards. So.
I mean, I that is definitely something to consider. I will
Mm-hmm.
not shoot that idea out of the air entirely.
Okay.
Um, but in interest of time, I'll keep moving because I have a lot of code to get through.
Sure, sure. Let's go
Um,
for it.
I print the left value just kind of as a debug to be like, oh, this is what's happening. So now I get into my corner logic. My corner logic is broken up into three pieces.
Mm-hmm.
So first of all, if front, actually, I'm really proud of this piece. If front is less than 0.5 and not self dot double check, I publish twist, which makes it stop, and then I set double check to be true. Um, then I say if front is less than 5 and not cornering and not post cornering, and there's been a sufficient delay since last corner and self double check, then it initiates a corner. I put this blurb here because I was running into an issue where noise in the LiDAR scan was causing it to corner for literally no reason. So what this means is that you need to have two consecutive LiDAR scans back to back that both say, okay, there's a corner ahead of you before you actually corner, which I think is a really neat solution.
Okay, so what's the
Um,
spacing between those two consecutive ones? What's the time?
what's the what?
The time
Oh,
difference.
it should be however long, it should be 0.5 seconds if I'm not mistaken, because that's when the timer calls this function again. And I
Okay,
mean,
okay.
you're probably plus or minus a little more just for the program to actually get down to this part of the function
All right,
again.
all right,
Um,
all right. I see.
so then from there, if self dot cornering, this is the logic of it like actually turning. Um, and if it's turned for long enough, it says, okay, I finished. And it changes a whole bunch of Booleans, sets a timer, and then if it's in post cornering, I used to have it so that it would drive forward slightly to kind of help pull it out of the corner, but that ended up just making it run into things. So I commented the bit that published that
Hmm.
because I knew that this velocity was the same that was being published all the time,
Hmm.
anyways, when it wasn't cornering.
Right.
Um, and even then, I'm pretty sure I set msg.linear or that MSG gets set to twist at the start of the function anyways, and then it just returns. If elapsed is less than this, meaning it'll hit it again,
Mm-hmm.
but if elapsed is equal than greater, it says cool, post corner complete, post cornering false, and then that's the whole corner cycle. It detected the corner, it turned through the corner, and it did a little bit of post cornering where it sat still for a couple seconds, which I also really like, and kept the whole sit there still for 2 seconds because it gives time for the LiDAR data to update.
Okay.
Um, before that happened, I was running into an issue where after it cornered, it would react based on stale LiDAR data, which was also causing it to run into things. Not great.
Okay. Okay.
Now we get into the actual wall following logic. The first thing I do is I set the linear velocity on x of 0.1. This is just an implementation specific that I chose kind of arbitrarily. I'm like, that's a good speed. Sure, why not? And then just built the rest of my code around it.
Did you test it
Um,
at least? Did you test to figure out is it actually a good speed? Right.
um, yeah, I mean, for a while I was playing around with it going slower, which would give it more finesse. But another thing I considered was, well, okay, I don't want the first 20 minutes of my presentation to be the robot um, like driving in one loop because it was going really slow.
Mm-hmm.
And zero point 0.1 seemed to me about the right mix of, okay, it's slow enough that it can react with fidelity and grace and it can correct itself meaningfully, but
Okay.
it's not so glacial that I'm just going to be sitting here on my hands for 20 minutes watching it like piddle along.
Mm-hmm. Okay.
Um, so First of all, I should probably go down to these three conditions. If left value is greater than this, and I'm not already turning left, then I set turning left. I set an angular. I do the same thing for the right. And this was actually a really interesting logic problem because when the robot needs to go further away from the wall, you can't have it constantly publishing a velocity that causes it to turn because that'll just make it go in a big circle,
Yeah.
which is not what I want. Rather,
Yes.
I want it to turn slightly and then go forwards for a few cycles and then potentially readjust.
Okay.
Um, so that gets into um, these things where it's like, okay, if this turning left Boolean is set, that means the robot has turned slightly left. I guess left is this way for me.
Right.
And then it's like, well, okay, I'm just going to cycle. I'm just going to return. Um, and so what it is I use left cycles to keep track of how many times it's cycled through. Once that reaches 3, elsewhere in the code, I have code to be like, oh, I'm going to reset, and this now means I can turn more. I also put a fun piece of logic in of, okay, if ever I'm turning left, um, and my left becomes less than 0.3, that means I don't need to turn anymore, no matter what. Like, stop turning, like, reconsider everything. So left cycles automatically get set to 3, which is the number of cycles that I have it going for. So it breaks out when it gets down to here, because it's like, oh, if turning left and left greater than or equal to 0.31, and self.left cycles equals 3, excuse me, then it resets, making it such that it can now decide, okay, do I still need to turn more left? Like, have I accomplished my goal yet? Have I reached the threshold? I mean, if it's hitting this, then it's obviously not.
Mm-hmm.
Actually, I guess this is just it resetting. And then once it resets, it gets down here to this block again and decides, well, okay, do I need to turn left more? The same thing happens for going right. I just figured I'd explain it with one of the two to be a little less confusing.
Yeah.
Um,
There is a lot of
finally,
moving parts there.
it's a lot of moving parts. I'm sorry if I explained it poorly.
Okay.
It was
You know, why I'm saying there's a lot of moving parts there is because would it not be easier for you to implement some type of controller, right? I'm just thinking in broad spec here, right? But maybe it would help if you think about it that way. Um,
yeah. I mean, I would choose to defend my implementation as um, I PID controllers and the like are not something that I'm super familiar with.
okay,
Um,
I
and
understand
when I
that.
came to this part of the project, my first thought, well, okay, not necessarily an excuse, more of a this is why I did it the way I did.
Yeah,
Because
okay.
I'm like, okay, I could spend a week teaching myself PID controllers,
Yes.
or I could sit down in an afternoon, crank this out, and have it work basically just as well.
All right. So,
Um,
basically, what you're trying to do was to like handle every other branch that your robot would have to, that it would the situation in which it would get into. You were trying to handle that as a separate branch in your loop, right? In your if statements.
um, really, there's only three states that the robot. Well, okay, I guess there's if you consider each linear combination of Boolean values to be a state, there's a lot of states.
Yes. Yeah.
But if you
That's
consider,
good
okay,
because why I'm saying that is I'm also looking at the number of things that you have to keep into consideration whenever you want your robot to make a corrective measure, right? So,
hmm
so I'm thinking if you would like enumerate those things, there will probably be quite a lot. That's why I'm thinking your algorithm is this
yeah,
big,
no,
but
I
yeah.
mean, I totally agree. It isn't pretty and it's probably not efficient. Um, but at the same time, it's what I knew how to make work out of the box.
It's yeah, yeah.
And
I think that's the
um,
most important thing, right? Being able to get it to do exactly what you want, right? It
mhm.
could be improved, yes, but I think for that, I would say like it's a it's a good thing. It's a
Yeah, yeah,
way that you've managed to get to work. So that's appreciated on its own, right?
yeah.
Improvements can
It's
come as we go. Yes.
of course. And then finally, I just have a little block here of if it's within 0.29 to 0.31.
Mm-hmm.
This is it staying in the ideal margin. So I basically tell it, cool, just keep going straight. Don't change anything.
Mm-hmm. Okay.
Um, which, yeah, doesn't, it usually like weaves back and forth a little bit more.
Yes. Yes.
Um, it doesn't always stay perfectly in that margin, but I've seen it stay there for most of the length of a wall,
Right.
which is kind of neat. At the end of all of this, I publish MSG because that's based on what happens in all of this logic. The message value gets set. I used to have a time.sleep. I just found that that made it jittery and didn't offer a meaningful benefit.
Mm-hmm.
So I commented that out. And also, I set waiting for scan to be false. Um, I feel this is, now that I think about it, a failure of nomenclature because it should be this indicates that I have consumed the most recent LiDAR scan
Mm-hmm.
and that I'm going to need another one before I can do something else.
Mm-hmm. Tell me something. How did you? What was your form of figuring out that you are receiving stale LiDAR data? How did you check for that?
So what I did in, is it laser scan? Yeah. So down here in my laser scan callback, I take all my data and I, at the very end, set self waiting for scan to be true.
Mm-hmm.
Um, ignoring the variable name, which in retrospect I probably should have changed to be more reflective of what it's actually trying to tell you.
Mm-hmm.
This says I have new LiDAR data. If I then go all the way back up to the top of my command velocity callback, if not self.waiting for scan, it stops and returns. This basically means that unless the LiDAR scanning logic has run at least once since the last time the robot moved, it's just going to stop and do nothing while
Okay.
waiting for that scan. And down here, where I set this to be false, this is me consuming the LiDAR data and saying, okay, I'm going to need more new data before I move again.
Okay. Okay. I see what you mean.
So, yeah.
All right, Matthew. I think that's all the time we've got. But thank you so much. It's been
Of
wonderful.
course.
And
Yeah.
all right. Just hang on one sec.
Of course.
All right, everyone. This was Matthew's presentation, and would like to thank him for coming here and explaining in detail what he had to do and giving as much insight into his implementation. And we highly encourage all those of you who would want to attempt this project, and also do not be fearful to try your own attempts. We will see if they can get the robot to do what they have to do. And very, very warm congratulations to Matthew for such a brave approach. And until next time, keep pushing your